colleague Damian Rössler, CNRS and Université Paris-Sud, will speak about conjectures on logarithmic derivatives of Artin L-functions.
Thank you very much.
I would like to talk about some conjectures that I made with Vincent Maillot, my collaborator, a long time, a few years ago already. So these conjectures try to we try to give it a geometric interpretation for the logarithmic derivatives of Artin L-functions of CM fields. And so let me write that on the blackboard. So everything that I'm talking about, as I said, is joint with Vincent Maillot. And and so the purpose, so to give a geometric meaning to the expression L prime chi 1 minus n divided by so more precisely, so k is an irreducible Artin character of a CM field. And we have n is larger or equal to 1. So it means we attempt to in fact, to give a conjectural. I mean, this is really largely a conjectural framework to this expression. So this means it's at negative integers. The evaluation of the logarithmic derivative at negative integers when it makes sense. So this has to be non-zero, of course. So that's so before I describe the general conjecture, so the plan of the talk is I'm going to give you some examples of such interpretations that as they appeared in the literature historically, and then I'll talk a little bit about Arakelov theory, which is the tool that allows us to provide to formulate a general conjecture, and then I'll explain how. I mean, I'll just give an outline of our use of Arakelov theory which explains how we obtain our conjectural formula. In fact, I mean, using Arakelov theory leads to more than just a conjectural formula, because it leads to proofs in many cases, of course, but not at all in the general case. In fact, mainly, of course, that's what many people might be interested in. I'm warning them. The Arakelov theory approach says very little about the non-abelian case. So it says something, I mean, basically we can say something in the case where it's a Dirichlet character. So the really interesting case where it's a non-abelian Artin character is wide open. So, so the basic, and
you are not qualifying for this.
You're disqualified.
What is the first historic example of such an interpretation? So you have, so the first example is the so-called Chaular-Selberg formula. And first example, I'm going to give you a whole sequence of examples. So it's the, and in fact, this should not really be called the Chaular-Selberg formula, although it's mostly known under this name. It's the Lurch. This formula is actually due to Lurch. who proved it 50 years before. It's so it's actually not. And so this formula, I mean, there are many ways to. It says something about the periods of elliptic curves with complex multiplication. And in pedestrian terms, it relates them to special values of the gamma function. But you can formulate it a bit differently. That's what I'm going to do here. So you take E, so Q bar, an elliptic curve with Cm by K, where K is a quadratic imaginary extension of Q, and yeah, with discriminant minus d, say. And well, then it gives a formula. In fact, this is a very precise form of the Charles-Selberg formula, which is due to, well, in this form, it's due to Colmez, in fact, to Pierre Colmez, which says that so the Faltings height HF of E, so that is, this is the Faltings height that appears in the proof of the Mordell conjecture, the Faltings height of an abelian variety, is equal to minus 1/2 of so zeta prime q minus 1 zeta q minus 1 plus and plus 1/4 log d. And yeah, and of course here chi is the only non-trivial, so odd Artin character of k. So that's so in fact in this case it's a Dirichlet character. And so here you see so here you have a logarithmic derivative, and yeah, and that is basically, historically, this is the first example of what I call the geometric interpretation of that. That is, you relate it to quantity which is computed on an algebraic variety. And yeah. Yes, and just while I'm think about that, so let me also put things straight. You see, when we interpret such values, we are outside the realm of the Bailinson conjecture. The Bailinson conjectures. the Bailinson conjectures, they predict something about the first non-zero value. This says something about the subdominant value, because this value here is subdominant. So it's something that really falls out completely out of the framework of the Deligne conjectures or Bailinson conjectures or Stark, or any of those. And it also has a different flavor. It's much less. See, the Bailinson conjectures are very general formulae on the L-functions of any motive or any variety. This is very specific. This is it only makes sense for CM number fields, and then we relate it to a specific geometric object, which in fact carries an action of that CM field. Like here. Okay, so this is an old example. Other examples appeared much more recently. So that's so there's the formula of Bost and Kuhn. In fact, in this form, this is due to Colmez. And so this computes specifically an Arakelov theoretic invariant.
What was the result of there then?
Well, the thing is, just a moment, the result of left. In fact, to compare this precisely to the formula that Lurch gave is a little bit difficult because he computed an elliptic integral. Because to compute the faulting site comes down to choosing a differential, then you have to compute an integral. I mean, just to remind you, so the faulting height, I mean, suppose that E is defined over Q to simplify things. Then you choose omega, or say eta. Yeah. You know, a Néron differential, say, sorry. Where E tilde is the minimal regular model of the curve. And, what I'm saying is actually only true. It depends. If it's actually what you usually write as the faulting site like that, you have to suppose that these curves have semi-stable reduction everywhere. Otherwise, you have to pass the function. And then, in fact, HF, semi-stable, is equal to minus 1/2 of log of 1 on 2 pi of the integral, and now over E of C, of eta wedge eta bar. So it is an integral, and in fact, I mean, in this case, when it is CM, this is an important distinction. When it is CM, this integral is a period. It is not true in general. I mean, faulting site is not in general related to the periods, but in the CM case, this really is a period. And then, I mean, you obtain ultimately, I mean, an explicit elliptic integral, which he then computes in terms of values of the gamma function, and the values of the gamma function are connected to this via the Hurwitz formula. But now, I mean, of course, in this process, there are lots of logs of prime numbers that appear, and I cannot exactly identify them with. But of course, you can do that. It's a geometric problem.
I'm sorry. So you said that chi was the Dirichlet character of k. Is that
of k? Yeah.
So there's no e on the right side. Okay.
No.
No, there's the discriminant.
Discriminant was the discriminant of k, right?
Of k.
So there's no elliptic curve on the right side. So e has to be.
That's right. There's no elliptic curve anymore. No.
Okay.
I mean, it depends only. In fact, the formula says that it depends only on these data. Sorry. In fact, this is you must be specific. It's by OK. It's the maximal order. I mean, of course, you're not allowed to change this. The faulting height is not invariant under isogeny. I mean, you have to. Yeah. So the formula of Bose-Kuhn, I mean, that one computes an Arikhelov theoretic invariant, this omega squared of a modular curve. So I'm going to be vague here on purpose because I don't want to define too many objects, but so you take x of n and you see it as a curve of a Q, I mean the usual modular curve. That means the fine moduli space for elliptic curves with level n structure. And well, then there is an invariant, this omega, you write it omega bar squared, xn. This is an invariant of Arikhelov theory, and it is a real number. And this, well, then there's this formula that Bose-Kuhn proved independently in the early 90s, which says that this is the same as the degree of the bundle of modular forms multiplied by the following quantity. So it's 1/3. Yeah. And then, I mean, then comes, in fact, q log q. Means there are this is some log p's multiplied by rational numbers. And these, in fact, I mean, can be made very precise, but then you have to choose your model. And you can, of course, simply take the minimal model, but I don't want to make specific choices of models here. But depending on which model over Z you choose, then I mean this is going to change. This is basically the transcendental component of that quantity. I mean that is the transcendental if you take the exponential. I mean,
And by Xn now, so you mean the disconnected model? So Xn now, you mean the disconnected thing? So you're taking it over Q.
I actually mean the yes. Yeah, and okay, now I'm going to quickly mention other examples of these invariants. I mean, there's another example due to Brunier-Kuhn. This is, I mean, in 2000 around there, and that's for a higher dimensional variety. So you have. This case, you consider a Hilbert modular surface. Classifying abelian varieties, abelian surfaces. With, in fact, with totally real multiplication. Yeah, well, totally real multiplication. By a quadratic extension of Q. Totally real, by real quadratic extension. And here, I mean, they compute a higher dimensional. So here they have a formula that omega x cube, in this case, is minus 4/3 degree of the sheaf of modular forms. And this time they have zeta. And here again, I mean, depending on exactly which model you choose, you will have a variation. So here again, logarithmic derivatives. And this time it's a zeta function. Of course, it can always be expressed using the Artin L-functions. And I mean, just to convince you that these things really do occur quite often, there's also another example due to this is, in fact, in the recent book, by Kugler, Rappaport, Yang. But in fact, I mean, many other people are involved in that. I mean, they consider compact Shimura curves. That is, those curves which parameterize abelian surfaces with quaternionic multiplication by a given indefinite quaternion algebra. So I'm just so here you have compact Shimura curves, and in fact I'm not going to bother saying again this, giving all the definitions again, because as you'll see, the formula doesn't depend on any of these data. So and they compute that at omega squared, in fact it's quite similar to. So this is actually this is a difficult result. I mean, this is difficult. So, and here again, I mean, so they of course they are for these curves, the models are well understood, and they compute exactly the local contributions coming also from the bat fibers of the model, and that is actually a very tricky thing to do. In fact, I mean, you have contributions of the type log p, I mean, something like that, log p times p plus 1 divided by p minus 1 things, and this is a very tricky part of the computation. So as you see, the formula is very similar to the formula for modular curves.
So in the Hilbert modular surface case, people know how to construct one regular model, is that fair?
In fact, I don't. In fact, I don't know. I don't know actually.
So you can compute this omega cube without the regular model, I guess.
Yeah, no, I don't know. I mean, because the thing is, Kuhn considered that in his thesis, and then I mean he came up with this transcendental part, which never varies.
Right.
And this might have changed between Kuhn and Brunier-Kuhn. So I don't know which model, exactly what they.
Oh, right. But there is some singular intersection theory, I guess, right? But
yes, yeah, there is. But in order to make sense of that, though, you really need a regular.
I guess.
So yeah, so I no. Sorry, I can't tell you exactly what they did. I should know, but no. Right. Yeah, so I mean, it would be interesting, you know, when you see all these formulae, to have the most general formula, at least conjecturally, you know, that would specialize to all of these, and so that's and this is where, in fact, sort of unexpectedly, Araki-Love theory provides an explanation, but I mean, it's not at all something one could guess. I mean, and in fact, with Vassambe, we didn't, we just stumbled on that interpretation. It's not something we weren't actually looking for it. I mean, it's, yeah, in fact, the only person who actually thought that there was a connection was Jörg Kramer in Berlin. I mean, he had this idea that the arithmetic Riemann-Roch Araki-Love theory should, you know, be connected with these things. In fact, this is also why he asked Ulf Kuhn to compute this invariant for xn. But that's yeah. So I mean, just to for those people who never heard of Araki-Love geometry, I just want you to give you an idea of what that is, and what one tries to do there. In fact, I've been involved in these sort of I mean, with Araki-Love theory for some time, and as a consequence, I have more and more trouble explaining what it is. In fact, ultimately, I always come up with a new way to understand it, and I'm not sure myself I really know what it is. I mean, it's so, but basically, the idea is that Araki-Love geometry, I mean, tries to do something that people have been trying to do for a long time in some other forms, maybe. I mean, which is to, you know, the product formula, you know, on Q, for instance, saying that if you take the product of the non-Archimedean absolute values times the Archimedean absolute value of a rational number, that gives 1. This is a sort of fundamental compatibility between all the valuations of Q, or even on a number field. There's a sort of fundamental compatibility between the non-Archimedean and Archimedean places. And Araki-Love geometry tries to track down sort of every instance of this compatibility. You know, I mean, it tries to really understand the Archimedean valuations as sort of as if they were fibers of a scheme, as if they were sort of the fibers of a scheme over Z. So, so that's so exactly. So it's an extension from that point of view. It's an extension of scheme theoretic algebraic geometry. Where the Archimedean places are viewed as the fibers, but I mean this has to be taken with quotes, of course. I mean as fibers with quotes of compactified schemes. That is, schemes where you actually add those, artificially add in fact, add the complex solutions, of the set of Diophantine equations to the non-Archimedean fibers to obtain a sort of object which is the basic object of Arkelov theory. So, and so these compactified objects are supposed to should be sort of viewed as schemes over spec Z compactified, and spec Z compactified is of course just spec Z together with infinity. And if you want to get even, this might become sort of a bit mystical, but there's of course the field F1 behind all of this. The idea is that this object here is supposed to be, spec Z being affine, spec Z compactify should be then sort of compact. And therefore, a good compact curve over the field with one element. And therefore be a better imitation of what the situation you are in over function fields, where you can have abelian schemes, which might be even smooth over a curve which is proper over the base field. And this curve proper over the base field should be this. So, so all this is a bit vague, but so basically there's a dictionary which is very precise, which I'm going to, so more precisely you have the dictionary. So you take, so consider a scheme S over spec Z, which is, reasonably sort of tame, so that, which is proper and flat. And regular. And that implies that, in fact, the complex points of S are smooth, is a smooth variety. And, then you have the following sort of dictionary. And, or dictionary.
S is just regular.
S is regular.
S is regular, right?
S is regular. S is regular as a scheme, and it's proper and flat over the integers. So now you have the following dictionary. So for one thing, in fact, this is one of the basic issues. You have, a natural p-adic distance on say the points of S over QP. This natural p-adic distance simply comes from the fact that you take, if you want to measure the distance between 2 points on S of QP, you take the 2 points. By the evaluative criterion of properness, this is actually equal to Z of ZP. You take those 2 points, and then you look at, you reduce the mod P, and and if they don't coincide, then they're at maximal distance. If they coincide up to the order P or P squared, P3 and so on, the distance becomes smaller and smaller. So you have an explicit, in fact the p-adic distance comes for free once you've got the scheme of Z over Z, the scheme of Z. And this is not true, in fact this is not true of a S of C. If you take the complex points, there's no such thing as a natural metric on it. There's no natural neighborhood, a way to reduce mod P, a point over the generic, over the complex, complex solution of S. So what Arkelov theory does to solve that problem is to simply endow S of C with the metric, and that's part of the data. And so this here becomes a Kähler metric on the complex point. So you see that from the start it's very analytic. This Kähler metric should then morally play the role of the p-adic distance. And once you've said that, then you continue. So For instance, vector bundles, locally free coherent locally free sheaves on S, they become vector bundles yeah, you could say vector bundles V, say V. Vector bundles, and then you write V bar, and that's VH, where H is a Hermitian metric on V of C. So if you have a vector bundle, the Arakelov theoretic object is the same vector bundle, but you take its complex points, that's a holomorphic vector bundle, or even the C infinity one, and therefore you can, and there exists Hermitian metrics on such vector bundles. That is, each fiber is a complex vector space, and you can endow that with you can put a Hermitian metric on each fiber and let that vary in a C infinite manner. That again is supposed to be then the corresponding p-adic distance on the vector bundle. And then, you have, this is for K theory, then you have, if you want to take cycles, well then you have algebraic cycles. And they become algebraic cycles endowed with certain currents that have a certain compatibility with them called green currents. So that's with green currents. So again, a completely analytic datum. And and then of course, there's the question of
so is it always possible to give calorimetric on complex points in this situation?
yes, because it's projective. Oh, because I didn't. Oh, yeah, that's true. No, proper. Yeah, no. Good point. Yes. In fact, this is quite important. You have to suppose. I suppose that the theory would work quite well if you just put proper, but then you have to assume the corresponding variety is scalar. Yeah, and you have, in fact, you have, if you take the K theory of SP, that means the fiber over, simply the fiber over P of S, that will become, in fact, in the theory, it will become the Deligne cohomology of the fiber at infinity. That is the real Deligne cohomology, so not.
S lower P means
The fiber at P.
about the finite field.
Over a finite field,
Oh.
yeah. Finite. And you can, then there is in fact, I'm just going to now sort of converge to what I'm going to need. So the K theory of the whole scheme becomes the K theory of the whole scheme with a hat. In fact, hats means that you are in Arakelov theory generally. So if you put a bar, it means you have a metric. If you put a hat, it means it's an Arakelov theoretic object. And this K theory, this K0 hat of S, in fact has very similar relationships to the original one, but of course the generators will be Hermitian vector bundles, that is these vector bundles endowed with Hermitian metric. And then the relationship is not going to be what one could imagine, that is simply orthogonally split exact sequences, but it will be any exact sequence of Hermitian vector bundles, and then you have to throw in what's called a Bot-Schoen class. And this Bot-Schoen class measures to some extent, the extent to which the sequence is not split. So this is an analytic datum, and so this is K0 as S plus Bot-Schoen classes. This again is a completely analytic datum. Right, and you have, if you have a morphism between such objects, it's between, in fact, let's call this an arithmetic variety, is what. If you have a morphism between arithmetic varieties and you choose a Kähler-metric on the top, then you can define a direct image if f is smooth over the complex points, or is generically smooth, same thing. Then you can define a direct image, and this direct image, I mean, will be, yeah, I mean, the usual, if you have, say, f goes from S to T, a variety of the same type, well, then you have, you know, the relative Euler characteristic in the classical case of a vector bundle E, say. And and this is something that, for instance, lives in the K-theory of T. And here you obtain, so under these hypotheses of smoothness of the complex points, you, in fact, you write E, and this object here, so here you have to make also another hypothesis, which is that these are again then locally free. This is actually not such a, I mean, if you take, for instance, if you have here a flat map and the vector bundle has no higher cohomology, that's automatic. So if they're all locally free, you can endow these direct images with natural Hermitian metrics, which you obtain by integrating the Hermitian metrics of E along the fibers. And it appears that if you want to have a coherent map from, you know, between these groups here with hats, then you have to add formally something which you know, will live in this Bot-Schoen form class, and this is the T of H, and this is called the this is the Bismuth-Köhler analytic torsion form. And this is an object which might not be known to you, but this is the most complicated analytic object in this theory, as I see it. I mean, it's a, so this is a spectral invariant, and if you, this is it's a differential form, but if you take its function part, its zeroth part, this is what's called the Ray-Singer analytic torsion, and the same Ray-Singer analytic torsion is a regularized determinant on the eigenvalues of the Kodaira Laplacian of E. And it's defined in a paper by Ray and Singer at the end of the 60s, where they introduced that. And this is the relative form, which was defined by Bismuth-Köhler much later. But again, I mean, I cannot define any of these objects because that's it would take too much time for the. But so here there's the most involved analytic object, I mean, that appears in this theory.
So this lives also in K0 hat.
Yes, that's right. This will live in K0 hat T. And it is a theorem, a difficult theorem, in fact, which is
so what is T now? We have three T's. Now we have three of those.
No, we have only one big T.
One, yeah.
Where's the second one?
Then we have
The torsion.
Oh, yes.
And
Oh.
then
All right. In fact, I mean, it doesn't matter if I. Okay. Yeah, and here, so that the E is. Okay. Yeah, and of course now you have, since you have maps between K-theory groups, and in fact you also have, but now I'm not going to write any more of this dictionary, you have Chow theory, you know, of course, classically, and then you have the Chow theory with the hat, and this Chow theory with the hat, the generators are these algebraic cycles with green currents. And you have the same way as you have a Chern character, you know, which goes from the usual K theory to the Chow theory S tensored with Q, here you have the same. You have the arithmetic Chern character, which goes from this more complicated group to this group here. And of course, once you have all these data, if you know about Riemann-Roch theorem, you wonder whether there's a Grothendieck-Riemann-Roch theorem. So there is such a thing. So that's, yeah, so you have Grothendieck-Riemann-Roch. And here you have indeed, this is the work of many people. I mean, there's Bismuth, Gillet, Saclay, and then Foltings also. I mean, he proved a version of this theorem for surfaces and then outlined the proof in general. I mean, there's and finally, there's also, this is something that plays a role in what I'm going to say, is there's a fixed point formula, so a geometric fixed point formula. What I mean by geometric fixed point formula is the fixed point formula for coherent sheaves and coherent cohomology. And there is such a formula for when you consider automorphisms of finite order. And this such a formula lives in K theory, in equivariant K theory. And there is again, I mean here, this same thing, this is due to Köhler and myself. There's a version of that in Artin theory. And yeah, and all this, in fact, I mean the proofs of all these theorems are heavily based on the work of Bismuth. I mean, Bismuth is in fact the main contributor somehow to this theory, although he does not work in arithmetics. I mean, he's a yeah, so now I'm going to since there's not much time, I'm going to give you very quickly the sort of the yoga which leads to this to a formula, a conjectural formula which should explain all those occurrences of logarithmic derivatives. So yeah, so simply consider first. So let x on S. So forget the S I defined before, it's not going to appear again. So simply a smooth projective fibration and you suppose that S is regular and yeah, and you suppose that it's quasi-projective over a Dedekind ring. So for instance, Z if you want to. Well, now I would like to show you a formula which is the results from Grothendieck-Riemann-Roch and which can be understood as a relative Gauss-Bonnet formula, and which is quite remarkable just as such. I mean, we are not doing auricular theory yet. This is simply in a purely geometric context. So, I mean, let me just remind you. So, in this case, Grothendieck-Riemann-Roch, I mean, says the following. It says that if you take a bundle W, so W, a vector bundle on X, well, then it will compute the Chern character of the relative Euler characteristic. That means this quantity there, the alternating sum of the relative cohomology sheaves. And it computes it by computing, in fact, I mean, very often one writes it this way. It's not really an integral. This is just the functoriality of Chow theory. You have, so the tot class of the sheaf of differentials of X on S dual and multiplied by the Chern character log. And this is an equality in the Chow theory of the base, tensor Q. Right. I hope that this is not in the way of the Chow group here. Yeah, and so this is what the Grothendieck-Riemann-Roch theorem says.
So sorry, this is over a C or over K bar?
This is exactly in this situation. So S regular quasi-projective over Dedekind.
So over S.
It's true of, it's in, this is in S. This is an identity in S, yeah. The reason why I put these hypotheses is because of the definition of Chow theory. Chow theory doesn't always exist, but it exists in this situation. You can, of course, formulate more general theorems, but then you have to change the group. Yeah, and now simply take this theorem and plug, for W, put in the de Rham complex. So instead of W, you take an alternating, you apply this theorem to the de Rham complex. So what I mean by that is you take, you have the de Rham complex OX and so on. So you simply take the objects of the de Rham complex. The differentials don't play a role in this formula. Just take the objects and you apply this formula to the alternating sum of these. So that gives, and in fact, so I'm going to write it explicitly. It gives PQ minus 1 to the P plus Q, RQF no star omega P is equal to the integral x of S of C top of thank you, of omega xs dual. C top is the top trend class. So this is the formula that it gives. So in fact there, what's hidden is a certain calculation with characteristic classes. If you insert CH of the alternating sum of the exterior powers of the sheaf of differentials, and you multiply it with the top class here, you obtain the top trend class. This is called the Borel-Serre identity. But this formula has now this formula is in fact, if you take S a point, say C, so the spectrum of a field, this formula is more well known. And in fact, it's very often known as the generalized Gauss-Bonnet formula. So that the fact that the integral of the top trend class is equal to the alternating sum, in fact, of the Betti numbers, in this case, via Hodge decomposition, if you work over C. But this is really a relative form. And what's really remarkable here is that you see this term here, because you integrate a thing that is homogeneous in Chow theory, it lives in degree 0. So in particular, if you consider, sorry, I forgot to turn character here. So in particular, if you consider the part of the Chern character which is non-zero, you take part of the Chern character which is non-zero, L larger than 0, this will be equal to 0. So you have a vanishing statement. And so it says this, I mean, the non-trivial Chern classes of this alternating sums are 0. So and in fact, this is not at all trivial. This is a completely non-trivial statement. And it doesn't follow from any either Serre duality or anything of the sort. I mean, it's a... Yeah, and of course, I mean, this is already geometrically interesting. But what's interesting is to write down the Araki-Love theoretic counterpart of this relative Gauss-Bonnet formula. And since I have only 5 minutes left, I'm going to skip to the formula you actually get. Yeah?
10.
I have 10 minutes? Okay, well then. Yeah, so here you have this Gauss-Bonnet formula. Now what you might do, you might consider exactly in the same setting here, an equivariant situation. So suppose, so suppose now that there is a mu n action on xs. So that means it's a mu-n action. Mu-n is the group scheme of nth roots of unity. And we ask that there is an action of mu-n on X as a scheme of S. So the action on S is trivial. So that's the action by a diagonal Zool group scheme. No. Mu-n is just as anything. It's just that if it just so happens that the nth roots of unity are defined over S, if you want, and n is invertible over S, well then this simply corresponds to the action of a finite group. But in general, it's the action of mu-n. Well, in this case, you can combine, what you can do is you can combine the fixed point formula, which I haven't even written down. You can combine it, that is just, plug it into the Grothendieck-Riemann-Roch theorem and apply it to the de Rham complex. And in fact, then you obtain an equivariant form of this formula. Yeah. And this equivariant form is like this. I mean, it says that CH of and here you have to so now it's k element of z on nz, and you take zeta k ch here, and this is then equal to sorry, not like this. So that is the equivariant form of the Gauss-Bonnet, relative Gauss-Bonnet formula.
You have too many chunks. Sorry.
I have too many chunks. Oh yes, yeah, quite right. Sorry. Oh yeah. Yeah, like this. Yeah, and here zeta is a primitive nth root of unity.
So you do assume n is invertible? You say no.
Sorry.
You do assume n is invertible?
No.
No.
Because this is I'm simply saying that this is in CH of S tensor Q mu n. That's all. This is a. So let me explain. What you make is you make an arbitrary choice of a primitive root of nth root of unity, an arbitrary one. And now you compute the following quantity. First you extend this you tensor CHS over Q with Q mu n, so that you can multiply by a root of unity. And then you compute the following relative trace. You take here these sheaves here are mu n equivariant, so they actually split up as a sum of eigenvector bundles. Each of them has a weight, which is this weight k here, and you multiply that by zeta to the power k, which is in fact the eigenvalue which acts on that eigenspace. And then you compute the Chern character. So this is a relative trace. If you take the zero part of that, it's nothing else than the trace, if you were in the situation where you have a finite group acting. Remember that in most cases this will simply be a finite group. If you over C, just think of a finite group, you're fine. And so it says that this relative trace where is equal to this. And here the integral is over x mu n, and this is the fixed point scheme of mu n. So this is fixed point scheme of mu n. And so here again, if you take the part which is of the non-vanishing part, this will be zero. It's exactly the same phenomenon. So the consequence of all this story is that if you are in an equivariant relative situation, and you consider this relative trace, of all the Hodge bundles, and you take the non-zero part of the Chern character, that is zero. And again, this is not an easy I don't know any other way to prove this.
You need to know something about this fixed point scheme.
No.
But if it's not smooth,
It's necessarily, with our hypotheses, X is smooth. And then this is necessarily regular. This is necessarily regular.
but that's not enough to put those relative differentials there. Divide it in a different way, I guess.
Yes, no, you're absolutely right. Actually, it is enough if you are over a field of characteristic 0. But you're quite right. Otherwise, you have to put the relative tangent, the tangent cotangent complex. Yeah, that's right. But in fact, since everything here is generically smooth anyway, I think that if you put the corresponding coherent sheaf, that will actually be true. It will represent the cotangent.
But then it gives the fact that it gives a minimum degree. If you need a complex, then you will have several contributions. It does not give necessarily purely in codimension 0.
If you
need a complex.
No, that's true. That's true. But actually, I think the other contributions will live in degree which are below.
Well,
Yeah, and therefore they will go on to 0 anyway. Okay. Well, now I have 4 minutes to. You might really wonder how I'm going to get to Artin L-functions, but yeah. So now the point is, if you remember anything, this talk at the end, the issue is that you take this relative equivariant Gauss-Bonnet formula and you put hats on it. So you consider it in Artin theory. This is ultimately after some linear algebra, which gives this relative conjecture. So that's what. So since I have little time, I'm going to take this. So take this here. So now you take the arithmetic Chern character. Here you put all these. You endow everything with kilometrics. So you put metrics on everything. And in fact, and then you have to make this computation applying arithmetic Riemann-Roch and arithmetic Lefschetz fixed point formula, that is the Araki-Love theory versions of those theorems. You have to plug them in here. And in fact, what you obtain is, you obtain again exactly this quantity, where you can put a hat if you want to. But since this lands in degree 0, the fact that there's a hat or not is irrelevant. It's anyway something in degree 0. And you then have two analytic quantities that come in. And these analytic quantities are as follows. In fact, on this side, you have, of course, the analytic torsion form I was talking about. This is the terms of the relative de Rham complex, lambda minus 1 omega 1. And here, on this side, you have a purely cohomological contribution, which is, I'm going to write it here, the integral over x mu n of c goes to s of c of c top, and now comes the R genus, which is a certain additive cohomological class, and which contains values of logarithmic derivatives of Lurch zeta functions. So this is how we're getting close to L values. Okay, so you have this analytic quantity here. Here you have again the same geometric quantity, and there you have this purely cohomological quantity. So this is a topological quantity actually, but which lives in the analytic part. And now it is a deep result of Bismuth that this is 0. This quantity, the analytic torsion of the de Rham complex, vanishes, and this is a difficult result.
Any smooth projective variability.
Yeah, for any, even in the relative situation, yeah. And for a smooth projective variety of a point, there it follows from the definition of the analytic torsion and the fact that there's a sort of collapsing phenomenon. But it's not a duality, it's a collapsing of the eigenvalues. I mean, this is something. Okay, so this vanishes and you're left with this. And this then is going to be computed by this integral. And the R genus, I'm just going to define it and then I might write down the final conjecture and then I'll stop. So, yeah, so the R genus is Rg is an additive class, you know, which has the property that, so formally Rg of X for line bundle. Yeah, you have to. Yeah, and R tilde of Zx is equal to sum over m larger than 0 of 2 zeta prime of z minus m plus 1 plus 1/2 1 on m times zeta of z minus m, and this then multiplied by m factorial. And this zeta unfortunately clashes with this zeta, but this is the Lurch zeta function. So zeta of zs is by definition sum over of z to the power m divided by m to the power s. It's a Lurch zeta function. Right, so this is an additive characteristic class whose coefficients are given by derivatives of Lurch zeta functions and their values, and which appears here. Good. Well, now I'm doing overtime, so I don't have the time to write the formula in its final form. But from this, you can see where, I hope, you can see where we're getting, because here you have a linear combination of arithmetic characteristic numbers, and they're given by a linear combination of geometric quantities, you know, these usual Chern classes, multiplied by derivatives of Lurch zeta functions. So now if you consider this conjecture, in fact, if you apply this conjecture, now the point is you take this conjecture and you, for instance, apply it to an abelian variety which has complex multiplication by a cyclotomic field. So there's a finite group acting.
What do you mean conjecture? I thought this was
No. So that's a theorem in that case. Yeah, that's right. The theorem in that case. You apply it to an abelian variety with complex multiplication by a cyclotomic field. Well, then after some linear algebra, you will obtain a formula for the Folting's height of this variety. And this allows you to compute the Folting's height of, for instance, an elliptic curve with Cm by a quadratic field, because if you multiply the elliptic curve sufficiently by itself, it will have Cm by a cyclotomic field. And then this can be applied to modular curves for the case of the action of -1 on the fibers. It can be applied to Shimura curves. In that case, it's the action by a quadratic field. In the case, etc., etc. It gives back all these formulae. They all come back. But there's just one thing, and this is the main, in fact, issue as far as, for instance, for compact Shimura curve, you really get exactly the right formula. For the case of modular curves, there's this theory of logarithmic metrics that appears. This does not take into account singularities of the metric. So here, this formula gives the right answer, but is conjectural. So yeah. So now, if you want the exact formula, which gives, which you obtain after modifying this in doing some linear algebra, you have to look into my paper. So thank you.
Thank you. Are there any questions?
What is the geometry you foresee for for non-abelian Artin L-functions?
Well, in fact, no. I mean, the thing is that we actually developed this also with Massamayo a lot because we hoped we would be able to tackle the non-abelian. But apparently, there's a sort of uncanny link between abelian and compact group acting. I mean, as soon as it gets non-abelian, that means, for instance, I mean, you have non-compact, I mean, that is discrete groups, I don't know, acting, and you just have no control anymore.
You have equivariant Riemann-Rochs for many
well, even in the geometric case, the equivariant Riemann-Roch theorems, they would be for actions by algebraic groups, for instance. Whereas, I mean, if you have a CM field acting, I mean, there's no way to compare that with an algebraic group. I mean, it's not a...
Actually, in this respect, I'm puzzled by this formula. Maybe you can explain. It's that when you do equivariant cohomology, typically when you have localization on the fixed set, it's because the group is connected in some way.
That's right.
But here your group is not. So why do you localize?
Yes, well, it's a good remark, because if the group is connected, you have even stronger results. You have the Bott residue formula, for instance, which tells you that if you have, for instance, an action by a torus GM, if you're in a GM equivariant variety and you have a GM equivariant vector bundle, you can compute all its Chen numbers on the fixed points. But here,
you don't have the one-dimensional orbits or something like this. Just the fixed points.
Just the fixed points. Yeah, I think. But here it's weaker because here you don't. So that would amount to computing this basically. Whereas here you have to weight this. You compute only the trace. If you want, I mean, if you had a GM group acting, you could apply this formula for zeta getting close to 1 on the circle, and then it would converge to 1, and you would have a localization formula. But that you cannot do if you have just a finite group. It stops. You remain with the weighted formula.
Can you explain at this occasion what is the lower k here in the omega b relative? You put a lower k.
That's right. The lower k is if you have an action by mu n. In fact, an action by the diagonal mu n is diagonalizable, and the action, the representation theory of a diagonalizable group, that's simply the grading under a mu n module is simply a z on nz graded module.
So what is omega b x over s parentheses lower k?
So that's the direct image, the qth relative cohomology sheaf of omega pxs, the pth root of differentials. This is an equivariant locally free sheaf.
So the lower k, the parenthesis is wrong here.
It's for the whole, yeah, if it's true. I mean, it depends how you,
Confused what you meant.
if you want, it's for this object.
That means you take the lower k on the direct image.
On the direct image.
Okay, thank you.
Yeah, absolutely.
And lower k means that you are taking homology with respect to these characters or not?
Well, it's a
Doesn't
very.
matter.
It doesn't. No, it doesn't matter. It's a very. Just, if you have a finite group, it's just the decomposition on eigenspaces, and it's the eigenspace for zeta k. Yeah.
Again, unless you are in same characteristic as the exponent, then the homology will not be the same as in
Yes, but not if you use mu n.
Okay.
I mean, this is true if you have a finite group acting. Then you get into trouble, I guess. But if you have mu n has a uniform, if you're the representation of mu p over fp is still the same. I mean, it doesn't.
But here dual of mu n,
Yeah,
same
yeah.
as that.
I have a sort of a very vague question that, so in the beginning you said that your conjecture is not as general as Bayes' and applies only in special situations and mostly over CM fields. But now, well, I can't see this in the general framework you presented. So somehow these objects become computable only in special situations or what?
Well,
function.
Yeah, okay, but still.
yeah, I mean, this, for instance, says something like, basically, if you, after you've done all this yoga of transforming this into different, something that's compatible with the expressions I gave at the beginning, you see that basically what it says is, if you have a family of motives, say, a family of motives with a polarization, so there's polarized motives, well then the Durand bundles of the motive are endowed with a natural metric, in fact, because of the polarization. And if now this motive is a CM motive, it's a family of CM motives, well then these Durand bundles, they will be decomposed into a family, into a direct sum of variations of Hodge structures, which each have CM by some subfields of the CM field. Okay, and what this says is that if you compute the arithmetic Chern numbers of these variations of Hodge structures, they will be related to the logarithmic derivatives of the Artin L-functions of the CM field. And in particular, of course, this is true for weight 1, and there you get abelian schemes. But it says that it should also be true for higher dimensional motives, and then the formula is similar, but will differ and depend on the Hodge structure.
But here this should be related to something you said before, which is that if you do not have a CM situation somehow, you can compute everything, but you find 0 equal to 0.
In the geometric situation. It's true. I mean, in the geometric situation, in fact, there you obtain that this is 0 in CHQ, so it says it's torsion object. And of course then you might wonder what is the order of the torsion. I mean, and I made a conjecture with Vincent about such things, about the order of the torsion. But this is also very mysterious. I mean, this is,
Other questions? Okay, well, thank you very much.